Okay, so up to this point, we've talked about the principal quantum number, the azimuthal quantum number, and the magnetic quantum number. But if you've been keeping track of things, you might wonder, what about the electron spin quantum number, m sub s? What's going on with that, and what is it for? Well, we talked about it as describing the actual electrons within the orbitals. The first three describe the orbital, or this particular orbital that the electron may be in, but m sub s describes the electron. Now, if we look at a hydrogen line spectrum, it looks like it's just 4 lines in the visible region. But if we were to zoom really finely in, what we would see is actually each line is split into 2 lines. And that was another confusing thing, something that the simple Bohr model didn't explain. And so where that comes from is actually the fact that electrons can have spin associated with them. And it's a little bit confusing to explain, but simply imagine that electrons can be spinning either clockwise or counterclockwise. And we refer to these as being spin up or spin down, but essentially imagine that there's only 2 possible spin states for an electron. And if that's true, then when an electron in one spin state jumps from one orbital to another orbital, it will, if it's jumping to a lower energy orbital, it will emit light, but at a certain wavelength. But the others, if an electron with the opposite spin is jumping from that same orbital, will also emit light, and it will be at almost identical wavelength, but just slightly different. And that is where those 2 lines come from. Now, Wolfgang Pauli is the one who's credited with this discussion on electron spin. He was a Nobel Prize winner in 1945. And he formulated something that's known as the Pauli exclusion principle. And that is essentially just that no 2 electrons can have the same set of 4 quantum numbers. So you might wonder, why would electrons have sets of quantum numbers? Well, that's actually what the whole point of the quantum numbers is. It's to describe the electrons, not the orbitals, but to describe the electrons. So the first three quantum numbers describe the orbital that the electron is in, and the last quantum number describes the electron spin itself of that electron. What falls out of that then is that every orbital can only hold a maximum of 2 electrons. And those 2 electrons must have opposite spin. So they must have different values of m sub s. Since there are only 2 possible values of m sub s, then any particular orbital would have the same first 3 quantum numbers. And the only difference for the electrons inside would be their spin quantum numbers. So you can only have 2 electrons per orbital. What does this allow us to do then? What this allows us to do is write a description of the actual position of the electrons. So we may not know their exact positions, right? That comes from the Heisenberg uncertainty principle. But we can know what orbitals those electrons are in. And so the way that we do this is by writing something known as an electron configuration. And if you are terrified, having heard that term before and not having understood at all what it meant, I will try to make it very simple as we go along. It's simply a listing of all of the electrons in an atom with their corresponding orbitals, with what orbital those electrons are in. And orbitals are filled when we start to draw or write out an electron configuration. We take the total number of electrons we have in the atom, which we can just get from the periodic table, the atomic number. And we start to fill those, we start to put those electrons into orbitals, say, you go here, you go here, you go here. And we do that by filling the lowest energy orbitals first and only putting 2 electrons per orbital, and then list things out. So here's our energy diagram reminding us of the relative energies of the different orbitals. We can see that the 1s orbital is the lowest in energy. And so then here's some examples. Let's say that I started with lithium. If I look on the periodic table, I'll see that the atomic number for lithium is 3. And so it has 3 electrons. Well, I'll first put 2 of those electrons into the lowest energy orbital, which is the 1s orbital. And then I move on to the next lowest energy orbital, and that would be the 2s orbital. So I only have one electron left. I put that one electron into that orbital. When I write the electron configuration, I write something very similar. I simply designate it slightly different. So I put the energy level, and then the orbital type, and then in superscript, I put the number of electrons in that orbital type. So here it's just 1s2, 2s1. Because there's 2 electrons in the 1s orbital, 1 electron in the 2s orbital. If I move over to boron, which has 5 electrons, I'll just first fill the 1s orbital, then the 2s orbital, and then I've got only 1 electron left over, so I put that into one of the 2p orbitals. And all 3 of the 2p orbitals are the same energy. Remember, they're degenerate. So it doesn't matter which one I put it into, I just put it into one of them. And then I would write this out as 1s2, 2s2, 2p1. Now, it might be helpful to note that the superscript here is just the number of electrons in that type of orbital, not simply in a single orbital of that type, but in that type of orbital. So there are 3 p orbitals. So I could have a superscript all the way up to 6, where I would be putting 2 electrons in each orbital. All right, so we've got this so far, but what happens when we come to something like carbon? Carbon has 6 electrons, so I would put 2 in the 1s, 2 in the 2s, but then I have 2 options when it comes to putting them in the p orbitals. So I can either put 2 in the 1s, 2 in the 2s, and then I could pair them up in one of the 2p orbitals, or I could put them separately in the 2p into 2 different 2p orbitals. And which way do I do it, and which way would I know? Well, this is where we come to a rule that's known as Hund's rule, and it simply states that we fill all degenerate orbitals, so ones of equal energy, we fill them singly with 1 electron. We fill them with the same spin. So each of those electrons, when we put those electrons in, they all have to have the same spin as we're putting 1 electron in each of those orbitals. And it's only after we put 1 electron in all of the degenerated orbitals that we then go back and start to pair them up if we have extra electrons. So in this case, carbon should look more like this here on the right. However, its electron configuration would simply be 1s2, 2s2, 2p2. When we write the electron configuration, it doesn't make a designation, it doesn't make a distinction about which p orbitals the electrons are in. So here's an overall example of kind of the orbital diagrams and then the electron configurations for a whole number of elements. So carbon, right, it looks like this, the orbital description, and then the 1s2, 2s2, and 2p2. Nitrogen, you'll notice we put 1 electron with the same spin in each of the 3 degenerate p orbitals before we would pair. Now we don't have anything to pair because we're out of electrons at that point. And so we get 1s2, 2s2, and then 2p3, where it's just the number of electrons per orbital type. And then it looks like we've skipped, so beyond nitrogen would be oxygen. You would simply start to pair, you would add that extra electron into this first p orbital here, now with the opposite spin. Neon or sodium, you can see the examples here of how we would write those electron configurations. So let's do a few examples real quickly. What's the electron configuration of sulfur? Very first process in writing electron configurations is first, find the total number of electrons, which you just get from the atomic number. So if I look at sulfur, sulfur has 16 electrons. And I'm just going to start at the bottom of my chart, start working my way up, filling in the different orbitals. So we just start at the beginning with the 1s, and then we just keep going. So here we put 2 in the 1s, so we get 1s2, then 2 in the 2s, it's 2s2, then 6, we go 1, 2, 3, all with the same spin, and then we have to go 1, 2, 3 again with the opposite spin to fill that up to fill all of the p orbitals. So that's 2p6, and that uses up 10 of my electrons. I still have 6 left, so 2 go into the next 3s orbital. And then the remaining 4 go into the 3p orbitals, singly, 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 and then that last one is paired. And so I can write out the electron configuration as 1s2, 2s2, 2p6, 3s2, 3p4. So what's the electron configuration of calcium then? Again, always start with the total number of electrons, which is just the atomic number. So 20 electrons for calcium. We just work our way up the chart. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Vanadium has 24 electrons. We treat it the same way. Here we just work our way up. And you'll notice here that now we start to get into the d orbitals. We now have enough electrons to get all the way up to the d orbitals, the 3d. And if we were thinking about how those were arranged in the d orbitals, it would be, there's 5 d orbitals. They're all at the same energy. They're degenerates. We would put, if we had 5 electrons, we would put singly, 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 singly. And then if we had extra electrons, we would go back and pair. Here we only have 3, so we should have 3 unpaired electrons in 3 of the d orbitals. And just as a reminder, here's kind of our scale for the energy levels for the atomic orbitals. So this is hopefully helpful for beginning to write electron configurations.